So we'll see how this goes. So this is the topic for tonight, galaxies in motion. What you're looking at here is a simulation of a galaxy. This is a galaxy that's probably close to what our Milky Way looks like. We can't watch galaxies like this. We can only do this in a computer. And I'm going to talk about why that's the case and how we actually do make measurements of galaxies. But before I get into that, I just want to talk a little bit about myself. Selfish, I know, but I'm like Lauren said, I'm a PhD astronomer. I graduated from University of Wisconsin-Madison in 2009, and then I was lucky enough to do 2 postdoctoral research positions in Europe. I was in the Netherlands for 5 years and in the UK for 2 years. And then in 2016, I moved back to the US. My parents were very happy with me when I did that, and took up a position here at UC Santa Cruz and at UC Observatories. There's me at Keck Observatory. Lick Observatory isn't the only institution or observatory that UCO manages. We also help manage the Keck Observatory. That's where a lot of frontier science is done nowadays. Of course, you don't need a picture of Lick Observatory. You're here, and then this is the beautiful Santa Cruz campus. I do instrumentation development. One of the instruments that we're very interested in at the moment is called Phobos. It's a massively multiplex spectrograph. That just means that we can take lots of spectra of lots of things at the same time. And then I also write software for processing data that we get from telescopes. This thing called Pipet is what processes raw data that we get from a telescope to produce spectra that we then analyze to measure things like I'm going to talk about tonight. And then I was also part of this survey called MANGA, we like our acronyms in astronomy, that surveyed many thousands of galaxies to try to understand their nature, how they formed, how they evolved. And I'll talk a little bit more about that as well. Okay, so what are we going to talk about? So I'm going to start with the motion of our own galaxy to kind of level set us. Put things in perspective for what we're going to talk about next. Given what I'll talk about there, how do we actually measure motions in other galaxies, and what do these measurements tell us about the differences and similarities between the galaxies that we see in our universe? Are those motions correlated with other properties, like the ages of the stars that are in those galaxies, etc.? And I'm actually not going to get to that last one, but we'll come up with some ongoing mysteries along the way. This last one is important. You have a lot to live up to. The last session had tons of questions, so please interrupt me with those questions. I'm happy to answer them, or try to at least. Okay, so I'm going to start with this. What is this? What is that band across the sky? The Milky Way. Okay, so you'll notice that this is actually taken from Australia. One of the reasons it's interesting to look at the Milky Way from the southern hemisphere is you see that bright patch there near the top of the picture. That's the center of the galaxy. It's easier to see the center of the galaxy from the southern hemisphere because it's in the south. You can see Sagittarius, which is where the center of the galaxy is from the north, but it's always low on the horizon. I think it might actually be up tonight, and the moon is dark, so you might see the Milky Way. Here's an artistic impression of what our current best guess of what the Milky Way actually looks like from outside of the Milky Way. We will never see the Milky Way in this way because it's just so big. And I want to give us some perspective on where we are. So here's the sun. We're about 26,000 light years from the center of the Milky Way. The Milky Way is what we call a disk or spiral galaxy. It's distribution of stars and gases in a thin disk. It has these spiral arms, many of which are named. You'll notice that the ones are named on this side of the galaxy. That's because it's difficult to see stuff on the other side of the galaxy because it's so far away. The galaxy has what we call a bar in the center. That just means that there's a collection of stars that form this elongated structure near the center of the galaxy. It also has a bright core. All of this is made up of stars and of gas. The coloring there indicates kind of the type of stars that you see in each location. Toward the center, they're older stars. Toward the outside, they're younger, bluer stars. Like I said, the center of the Milky Way is about 26,000 light years from the sun. And we can also measure how fast the galaxy rotates. So if you look out and you measure how quickly stars are moving in our galaxy, we can come up with a plot like this. Don't be afraid, these are just data points, it's just a plot. You do use this to describe the data that we find and then interpret things from it. So on this left axis, I'm showing the rotation speed of the galaxy as a function of distance from the center. In astronomy, we use really large units, so this is in kiloparsecs, 10 kiloparsecs. Our sun is at 8 kiloparsecs. A kiloparsec is 9 quadrillion miles. It's a long way. And our sun is rotating at about 200 to, there it says 220 kilometers per second. That's fast. It's really fast. It's 500 miles per hour. If you were at the orbit of the International Space Station, you go around the Earth in 4 minutes if you're going that fast. Really, really fast. So why then can't we see things move? Well, the size of the galaxy, as I've said, is huge. It's 100,000 light years in diameter. Just to put that into perspective, the nearest star to us is 4 light years away. That's 100 light years. I can't draw 4 light years with any kind of length. I can only draw 400. So that's 100 times bigger than the distance between us and our nearest star, and the galaxy is that much bigger than that. It's a big place. And so given that, you can kind of now understand why it takes so long for things to rotate around the galaxy. So it takes us about 240 million years to go around the center of the galaxy once. That's about as long as the first dinosaurs appeared on Earth, was about 235 million years ago. We've gone around once in that time. Since the dinosaurs have gone extinct, we were about there. Humans have been around for about 250,000 years. We've gone not even that far. I can't draw 0.4 degrees. I can draw 4 degrees, that's 10 times longer. If you were to equate the time that it takes us to go around the sun with the time that it takes us to go around the galaxy, humans have been around for less than a day in a galactic year since. It's a big place, and things move fast, but it's so big that those appear slow. Okay, so first take-home point for tonight. Long-term monitoring of galaxies, we can't just watch them move. We're not around that long. So how do we actually measure motions in the sky? To describe that, I have to start with some physics. Who here has seen a spectrum? Well, there's one there, so everyone should raise their hand. But if you didn't raise your hand before, who's seen a rainbow? If you've seen a rainbow, you've seen a spectrum. So a spectrum is just a dispersion of light from white light into its individual wavelengths. And so this is shown in this diagram via a prism. And so white light from the sun is coming in at the left. The light is dispersed through the prism. As light goes through the prism, red light deflects less, blue light deflects more. And so the red light is at the top, blue light is at the bottom. The reason we do this is because it allows us to separate where that light could come from. And that's described here. So let's imagine that this continuum source is the sun. So at the top is that spectrum that I just showed you. It's basically featureless. You're just seeing the colors and intensity of the spectrum. But say that continuum source illuminates a cloud of gas, a cloud of hydrogen gas. There's 3 perspectives shown in this plot. One is where you're just looking directly at the continuum source, so you see the whole spectrum. If you're looking at the continuum source through the cloud, as the light goes through that cloud, it interacts with the atoms in the cloud. It causes excitations in the atoms that then cause the light to get absorbed and then re-emitted everywhere. So because that it's absorbed and re-emitted everywhere, you see dark lines specific to where hydrogen energy levels occur. These are specific to hydrogen. There are other lines for silicon, for oxygen, for carbon, etc. So when you see a spectrum like that, you know hydrogen is in that cloud. But if you're not looking at the continuum source, if you're looking at the cloud itself and not looking at the background light of the continuum source, you just see the light that was absorbed and re-emitted by the cloud. And so that's why you see black everywhere apart from what's hard to see in this screen, but you see individual lines. And those are the individual lines that are caused by helium atoms that are re-emitting the spectrum that they absorbed from the continuum source. So for a galaxy, all this is happening at the same time. The stars are in the cloud. The cloud is not just hydrogen. It's got oxygen, it's got nitrogen, it's got tons of stuff. And so you see both of these things superimposed on one another. And so this is what it looks like. Again, just data, don't be afraid of it. The left axis is the flux. That's the amount of light that's coming from each individual wavelength. And then the bottom axis is that wavelength. We measure In astronomy, we tend to think, at least in the optical astronomy, we measure wavelengths in angstroms, which is 10 nanometers. 0.1 nanometers, sorry. On the top is a spectrum of a galaxy that has strong emission lines. And so it's kind of hard to see, but there's actually black that's underneath that blue line. That's the observed data. And then what I've done is I've modeled that spectrum with a combination of stellar absorption lines, that's the blue, and nebular or gas emission lines, that's the red. And so you can see the red peaking up there. That's the emission from those gas clouds that are rescattering light from other sources into our line of sight. And then the blue is, you see the absorption from the blue, that's actually caused by the atmospheres of stars themselves. So as light comes out of a star, it passes through an atmosphere. It's very different from our atmosphere, but it's still an atmosphere. And that causes absorption at very specific wavelengths tied to the types of atoms and molecules that are in those stars. And so you can see some of them are labeled. So this line out here is oxygen. There's a bunch of H for hydrogen lines, another oxygen line, some nitrogen, sulfur. So these absorption lines are also measured. Here's sodium, here's titanium oxide, there's magnesium, et cetera, et cetera. So this is one of the kind of amazing tricks that we use as astronomers, is if you disperse light, you can measure the atoms that are in a galaxy that's so far away you can't even think of how far away it is. And this is one of the most amazing things to me. Yes?
How are you differentiating between the gases versus the atmosphere of the celestial object?
That is an excellent question. This thing pops sometimes, sorry. So I'm trying to be simplistic here. So as you noted, not all the emission from the gas is going to be in these confined lines, and not all the absorption is going to be from the stars. But there are certain absorption lines that are only found in stars, and there are certain absorption lines where only interstellar absorption occurs. So for example, this calcium line, we know that's both stars and gas. And so when you model this line, you can't model it only the stars or only the gas. You have to include both. But most of the absorption lines that you see really are dominated by the stellar absorption features. And most of the emissions you see is really dominated by gas that's not part of the star itself. Does that answer your question? Okay. Any others? Yes?
Does understanding the spectra help you understand how far it is, or just what it's made of?
It does. I'm not going to get into that tonight, but there's a correlation between the redshift of an object, or how where the wavelengths at which we measure these features, and the distance of the object. And so we use those terms interchangeably a lot, distance and redshift, and that's specifically for galaxies. That's not for like local stars in our Milky Way, but for galaxies we can make that correlation. Good question. Yes? Good question. So for where the lines occur, that's basically quantum mechanics. And so there's certain distinct levels or distinct transitions between how an electron interacts with its host proton in a hydrogen atom, and how those interactions happen says that there should be an H alpha transition at 6553 angstroms. And so we can do that in the lab. We can predict them using quantum mechanics and then measure where they land in the lab. For stars, because of these absorption lines, a lot of what you do for stars is you actually just observe a bunch of stars in the Milky Way. You assume those stars are the same here as they are in the other galaxies. And so you just fit those stars to the galaxy, to the continua that you see in other galaxies. So you're making an assumption there about what the other galaxy is made of. There's lots of optimization algorithms that are used. So when I fit the data with a model, I have to optimize that solution so that it fits the data as best as possible. So there's lots of computer science that goes into that. Yeah, those are the big things I can think of at the moment. Good question. Other questions? Okay. So that's one key thing, is spectroscopy. That's how we measure what is in a galaxy, and these fine features in the galaxy are really important for measuring motions because of the Doppler effect. Who knows what the Doppler effect is? I see a few hands. So here's a simulation of an object that's emitting light or emitting waves, but it's stationary. This is from Wikipedia, so you can go find it yourself. It's emitting light and it's not, or it's emitting waves and it's not moving. So it doesn't matter what direction you look at that object, you'll always measure the same wavelength. Okay? But if you set that object in motion, then as it moves in one direction, those waves all get compressed. And so the wavelength that you measure, if you're standing on this side because the object is moving toward you, has shorter wavelength or higher frequency. If you're on the other side, as the object moves away from you, those waves get stretched out. And so you measure a longer wavelength or a lower frequency. But importantly, if you're along this direction, you don't see that motion. You don't see that change because it's transverse to your line of sight. You don't measure the compression of the waves because you just don't see that compression. Okay, so how do we use this? Well, let's put this into practice. Here's a galaxy. We're going to observe it with this thing called an integral field unit. So what this is a group of optical fibers that we've packed together. Each of these optical fibers collects light from the sky, from the object, and it passes it to a spectrograph. That spectrograph then disperses the light and allows us to observe the spectrum at that specific position on the sky. So you see that hexagonal layout on the top image there, and we're going to observe it using that hexagonal layout of fibers. So let's say that I observe using this fiber here, and I see something like that. Those vertical black lines are what we call the rest wavelength of those features, the two nitrogen lines and a hydrogen line. And so because the observed spectrum, that red spectrum, is shifted to the right, they're at longer wavelengths, that means that that side of the galaxy, that bit of light that we've measured, must be moving relatively away from us. Okay? Let's do it from the other side. So let's say we do the same thing, but we use that fiber. So now, here's the vertical lines, there's the rest wavelength. Now the whole thing is shifted to the shorter wavelengths, to the bluer side. That means that that side must be more moving relatively toward us. So if we do that for all the fibers, it can look like this. So one side you get majority redshift, on the other side you get majority blue shift. So we can do that for all the lines. We don't just have to use hydrogen or nitrogen. We can do that for both the emission lines and the absorption lines. So we can measure different motions between the gas and the stars. And so this is one of the main tools that we use for measuring motions in galaxies. So that's your second take-home point for tonight. Our measurements of galaxy motions rely on Doppler shift. Almost always. That's not true, but almost always, at least for the purposes of this talk. Let me stop and see if there's any questions before we keep going. Okay. All right, so here's another galaxy. For the keen-eyed, you'll note that this is a different galaxy because the red side is on the bottom, blue side's on the top. It was the reverse for the other galaxy. And so what do we do with this data? We've got the measurements of motion, but they're all along our line of sight. Well, what we do is we start by assuming that it's a disk, that it's rotating. And so the reason it looks like this is that if I'm on the bottom, I'm coming around and I'm moving away from you. And so that bottom part is moving away from our line of sight. But then as I rotate up and I come back this way, now I'm moving toward you. And so it's away and toward, away and toward. Now, interestingly, I didn't say this to the previous group, but you notice how I'm doing this. So the disk would be here. But I can do the same thing here. So I can move toward you this way and away from you this way. So we don't actually know whether it's this way or this way. We just know that it's rotating into our plane. So we're going to measure. So we've modeled it. So now I can take that model and I can show a plot just like I showed before for the Milky Way. So here on the left is the rotation speed, and this is a function of distance. So now this is just on the sky. So this isn't in physical units. And I can show the difference between the gas and the stars. And they are different. I don't have time to get into why they're different, but the point is that you can measure the rotation speeds of these components of a galaxy using this approach. So what do we do with that? Well, let's start with something we know, something close to home. If I were to try to plot the rotation curve of the solar system, what would it look like? So here's that plot. So on the left, rotation speed, bottom, distance. I didn't say this the last time either. This is in a weird unit called AU. Who knows what an AU is? Astronomical unit. What is that? Distance from the sun to the Earth. Yes, we like our acronyms and we like our units in astronomy. Say again.
We're one. Earth is one.
Earth is one. Exactly. Number one. So the point here is that as you go close to the sun, you rotate really, really fast, and as you get further and further away, you rotate more slowly. Why is that? Mass. Where is the mass in the solar system? The sun. It's basically all in the sun. Jupiter, of course, has mass, but 99.86% of all mass in the solar system is in the sun. So as far as this plot is concerned, you can basically ignore the mass of the rest of the planets. It's all in the sun. And so this is basically just Newtonian gravity. You've got all the masses in the sun. As you go farther and farther away, the force of gravity gets less and less, and so you rotate more slowly. Now, if we compare that to this galaxy, they don't look quite the same, right? Here in the solar system, it peaks in the center and then goes down. It's basically the opposite for this galaxy. It's low in the center and then comes up as you go further and further away. Basically, this is telling us what the mass distribution is in that galaxy. And so for the sun, or for the solar system, all the mass is in the sun. And so as we go further and further away, we're not adding mass. We're not adding gravitational force that causes the planet to move faster. For the galaxy, the mass is distributed. It's not all in the center. It's actually throughout the whole galaxy. And so as we go out, we're picking up more and more mass that causes those stars to go faster and faster until it basically flattens out. And that basically looks like our Milky Way galaxy, the way, in gross terms, of first order. The Milky Way doesn't seem to come down as quickly as this galaxy, but some of that is observational effect. Yes?
There's more mass outside of the galaxy. Is there a black hole always
So those are two different questions. So that's the first one. So we do think typically that basically every galaxy has a black hole. Yes. That's not necessarily why that in the Milky Way, why it peaks up that quickly. Like in the Milky Way, you might think, well, there's a black hole, so that's why it kind of looks like the solar system toward the center. That's not, the black hole is much further toward the center, the effect of that. This is probably because of the mass concentration. There's a significant mass concentration in the center of the Milky Way that doesn't necessarily match this other galaxy. Is that, I think that, oh, right, and your other point about adding mass. Now, I didn't say this in the last group either. You've got some awesome questions. The reason this thing goes flat, we think, is because you have to add more and more mass as you get to larger and larger distances. But if you look at the galaxy, eventually you run out where the galaxy doesn't have any more light anymore. So where is that mass coming from? That's dark matter. That's one of the first evidences for dark matter, is the fact that this stays flat, meaning there must be mass there if gravity works, but you basically run out of light. So you run out of stuff that we can see that's in the galaxy. So there must be some kind of quote-unquote dark matter. Yes? Good question. Can you be more specific?
Like if you're measuring rotational, like planetary rotations, and maybe one of them is really, really fast compared to everything else, how would you account
So yeah, so you have to be very careful when you find something that's odd, that doesn't match either your prediction or match what you've seen in many other observations of similar type things. So there's two ways you can go there. One, you can just ignore it. That's not a good way to go. You can try to assess whether there was something wrong in the observations, or more interestingly, you can try to find an explanation for why that specific thing happened. So for example, you'll note in the rotation curve of the Milky Way, once you get past the sun, there's a lot more scatter in the points. Inward, there's less scatter, and the reason for that is how we do the measurements. And so inward, without going into a whole lot of detail, it's just easier to measure motions of rotation in the inner galaxy toward the center relative to us. It becomes more difficult outer. And so this plot isn't saying that the rotation speed of the Milky Way is just noisier in the outer parts. It's more a reflection of our ability to make those measurements at those distances. Yeah.
So how can the speed be different at a particular distance? This is very nice. So at certain parts in space, it's moves faster.
Yes. So are you talking about like the bumps and wiggles?
Like at a point, like at a line from a distance, I would expect it to be the same, right? All the objects.
Oh, yes. Yeah, so this is as a function of distance from the center. So it's an average of what the rotation speed is anywhere at that radius. Okay. Yes.
It's following a very weird pattern. It starts low and then it peaks up and it comes back down. And can you explain the pattern?
Yeah, so the basic explanation is it's tied to how the mass is distributed in the Milky Way. And so as you start in the center, there's a black hole, and so it peaks up high. And then as you go out, there's a really large mass concentration. So as you go out from that mass concentration, it looks like the solar system. So you accrue a bunch of mass really quickly, and then you don't accrue as much mass as quickly, and so it goes back down again. These bumps and wiggles, part of them are associated with, you could have a ring structure, you could have more mass in one position and then it goes down, so there's just fluctuations in the mass distribution. But also there's what we call streaming motions. And so the way that these are measured is you measure the motions along a specific line of sight, but that isn't just affected by the mass. Like as you've seen from like even this image, there's a spiral arm. That spiral arm has some mass associated with it, and so that will cause small deviations in the motion of the star as it moves through that. And so most of these wiggles are associated with some kind of mass perturbation.
And then so why doesn't it follow a pattern? I'm talking about mass distribution. Because I imagine if it's spinning super, super fast, like a pizza would spin fast in a factory, it becomes evenly distributed, right? So what are the differentiations for?
That is a good question, and it's something that's still continued to be studied. And the reason I'm saying that is because we don't really know what generates spiral structure. Most of those fluctuations are generated by spiral structure. We don't think spirals are, and this is getting a little off topic, but it's a cool question. We don't think spirals are like fixed structures in time. So as a galaxy rotates, that spiral arm doesn't rotate with it. Stars move in and out of the spiral arm, they go away, they come back. And so these fluctuations are just natural perturbations that come and go as the galaxy evolves. And so you're right that those things should smooth out over time, but for some reason they don't. There's fluctuations, there's impulses that happen in the galaxy, either by an interaction or by things that get scattered off of stars as they rotate around that cause those perturbations to come and go. Does that make sense? Yeah, okay. So let me ask, what kind of first order thing do you see as a difference between this rotation curve, let's just pick the gas, and of this galaxy and of our Milky Way? We talked about the wiggles, ignore the wiggles for the moment. We talked about the difference in the center, ignore that for the moment. What other big thing? It is dispersed, it's much tighter here. What about the level? Yes. So the bottom one rotates faster. So it's more like 320 kilometers per second, whereas our galaxy is more like 220 kilometers per second. Any guesses? Why is that? More mass. Exactly. So let's do this for a whole bunch of galaxies. And we won't plot mass, but we're going to make brightness a proxy for mass. We're going to say if a galaxy is brighter, we're going to measure its rotation speed and just see what it looks like. And this is a very old relation. It's almost 50 years old. But if you plot the brightness of a galaxy, so brightness increases, forget the units, they're annoying astronomy things. The brightness increases toward the top, the rotation speed increases toward the right, and you see this correlation. So even with a few galaxies in this very early study, we noticed that galaxies that are brighter rotate faster. More recently, this is still even 20 years old, we've got many more galaxies and this relation persists. And it's basically what we just said, is that galaxies that are brighter, they have more mass, and therefore they rotate faster. Yes?
In in that spectra, where would our galaxy be? Are we bottom, middle?
Yeah, good question. I'm trying to remember. I think we're something like 10 to the 10, and we rotate at 220. So this is in log units, which is kind of annoying. 2.3 is 200, so actually we're probably here. Yeah. Yes.
The size of the black hole in the center, indicate how fast or slow a galaxy will rotate?
That's an excellent question.
How bright it may or may not be? Like, why is it light before there's a black hole?
So let's look at this. So I don't know why I did that, but let's look at the top one for the Milky Way. We know there's a black hole in the center of the Milky Way. We haven't seen it, but you can look at stars that are very close to the center, and they whip around like crazy because it's a huge, massive object right there. So the reason we think there's a black hole in there is kind of a similar idea. You can measure the motions of stars near the very, very center, and you have to have really high resolution to do this, and they have really high velocities. But we don't see it because it's such a small component of the distributions of stars that are in there. And so it's not like the black hole dominates the center. It's just one component of many, many, many stars that are at that position, and so you basically can't see it. And it's also so small compared to the rest of the galaxy that it might affect things very, very close to the center. And because it's so massive, much more than it should. I mean, it's got a whole lot of mass, so it actually goes much further than a normal star would. But way out here, you basically don't feel the influence of the black hole. It's such a small, even for really, really massive black holes, it's still a small component of the total mass at that radius. Having said that, there are correlations between the mass of a black hole and things like the brightness of a galaxy. So somehow galaxies know, and this is one of the big unanswered questions at the moment, somehow galaxies know what black hole they have in them, even though they don't influence things that are way out there. Why is that? We think it has something to do with the formation process, that galaxies that are more massive get more massive black holes, but we don't know the detailed process. That was a bit of a tangent, but I hope that answered your question. Okay. Okay, so in this, I'm running slower than before. In this title, I say that brighter spiral galaxies rotate faster. And so I made that distinction, I emphasized that word spiral. So all of these galaxies are galaxies like our Milky Way, they're disk galaxies. So I have to pick a little rejoinder here and just talk about galaxy taxonomy. Has anybody seen this thing before? No? Do you know this guy? Yes? This is called the Hubble tuning fork. The reason it's called that is because of what it looks like, but he used this to describe his classification system for different types of galaxies. On the right, you have spiral galaxies. They're broken into two branches, but basically whether or not they have a bar. And then on the left, there's things we call elliptical galaxies. So those are galaxies that don't have a disk. They're more spheroidal. They're fatter. And they often don't have things like spiral arms. They often don't have much gas associated with them. Here's a more modern view of this. So these are images taken from, I think, the Sloan Digital Sky Survey. It's part of a project called Galaxy Zoo, where you can, as the public, go on and classify galaxies if you're interested in doing that. On the left, again, circled in red, are these elliptical galaxies. On the right are spiral galaxies. And now in this plot on the far right, we have these things that we don't know what to do with, so we call them irregular. Irregular galaxies, they don't match any of this. Okay, so part of the things we're interested in understanding this diagram is why do galaxies separate themselves out in this way? If these things rotate faster when they're brighter, is that also true of these things? And so in order to answer that question, I actually have to answer a different question, is how do we measure motions in galaxies where there isn't much ordered motion? They're more random. Instead of all the stars going in one direction, they kind of go all over the place. They're more chaotic. So I have to introduce this concept of velocity dispersion. So this is a simulation of stars in our Milky Way. These are stars that have measured motions that are currently stars that live near our sun, and this is a prediction of how they move around the Milky Way. One thing you immediately notice is even though they started in this kind of tight packed group near the sun, they're spread out all over the place. And the reason for that is because they've all got their own little individual velocities, their own trajectories that put them on their own orbits. And so if you watch this simulation, you'll see that they just go everywhere. And so how do you actually quantify at any given position? When you're not measuring just one star, you're measuring hundreds, thousands, millions of stars over a certain area. What are you looking at when you do that? And that's where this concept of velocity dispersion comes up. And so when you have our fiber on our galaxy, there's tons of stars in there, there's lots of gas in there. If they were all rotating in the exact same direction, here's an absorption line spectrum for those stars. It's 3 calcium lines. They have a certain specific width associated with each individual star. If they were all moving along in the same exact direction, they would have the same Doppler redshift, and so we would measure something that looked like an individual star, even though it's an aggregation of a bunch of stars. But we don't have that. The stars in that simulation, like I just showed, they kind of have their own little paths. They might all be moving in the same direction for these spiral galaxies, but they don't follow exactly the same orbit. There's some kind of dispersion to their orbit. And so if we just had these 5-ish stars that were moving around, and you add all those triplets that are kind of offset from one another, it would look like this. But of course, there's not just 5 stars. There's a whole bunch of stars that are in this little patch that we're observing with a single spectrum. And so if you add a bunch of those stars together, you add all their spectra together, they end up looking, again, exactly like what a single star would be, but their lines are much fatter. And that's because their motions are all offset and superimposed on one another. And so you measure the width of the line, and that is what we call the velocity dispersion. So it's a measure, the velocity dispersion is a measure of the randomness of the motions of the orbits, or of the stellar orbits as they go around the galaxy. Any questions? Okay. So let's do that for elliptical galaxies. Now I'm going to come back to why I'm making this distinction again. But if we, instead of measuring rotation speed, we show brightness again as a function of velocity dispersion. Annoyingly, these two plots show them in just like the previous one, they show them in a different orientation. But you still see this correlation. So brighter things, if they're spirals, they rotate faster. If they're ellipticals, they have higher dispersion. I'll point out this is also a 50-year-old observation, and we're still doing it today. Sandy Faber is an emeritus professor at UC Santa Cruz. The observations that were taken for this plot were actually from the Shane telescope. This is a very, very famous relation. And so, brighter elliptical galaxies exhibit larger random motions. And so coming back to this, we know that these things, for brighter ones of these things, they spin faster. For brighter ones of these things, they have larger velocity dispersions. And so that is the third takeaway for tonight. Brighter spiral galaxies rotate faster. Brighter ellipticals have larger random motions. Okay, let me stop there again and see if there's any questions. Okay, on we go. So why, I made this distinction between ellipticals and spirals. Why not just observe all of them, put them all on the same plot and see what it looks like? Part of the reason for that is that when you're doing specific studies and you're trying to understand individual types of objects, you want to start and confine your variables. And so instead of studying all galaxies, let's just start with a few spiral galaxies and see what happens. Let's just start with a few ellipticals and see what happens. And so once we realized that these relations they stayed, as we gathered more and more data for different spirals, that relationship held. So now let's do a survey where we're collecting data for thousands of galaxies, regardless of whether they're spirals or ellipticals or irregulars or whatever, and let's see what happens. So I was part of this survey called the Sloan Digital Sky Survey. That's what that SDSS stands for. part of the survey was the MANGA sub-survey. MANGA stands for Mapping Nearby Galaxies at APO. We like to embed acronyms with other acronyms in astronomy. So we observed 10,000 galaxies over a period of 6 years using this dedicated telescope. And I want to emphasize that, you know, even though it's me up here talking, you're hearing about all these different results. Most of these plots are not mine, and most of the work that was done for this specific survey was not just me. These are hundreds of scientists all dedicated toward understanding these galaxies. Okay, and so we took observations of all these tens of thousand galaxies, and because it's a spectrograph that has a large wavelength range, we can measure tons of different things. And so here, this is just a plot that's similar to ones you've seen before. So on the right are the spectra. On the left are maps on sky of different properties. The top should look familiar. This is the velocity field that we have been talking about. On the those squares on the velocity field point to these different spectra. So at A, you have that top spectrum. At B, you have this middle spectrum. And at C, you have this other spectrum. And so because you've got these observations at multiple different points, it allows you to study different things as a function of position within the galaxy, not just as a single center position. That top is velocity. The middle is the flux in this H alpha. If you took a look through the telescope before you entered this evening when the sun was still up, that was measuring and looking at the sun in the H alpha filter. And so that's kind of like what an H alpha view of this galaxy would look like. And this bottom diagram is telling you something about the age of the stars that are at specific positions in the galaxy. And so red here means the stars are older. And so if you're in the center of this galaxy, the stars are older. And then as you go in the outskirts, they become younger. On the very outskirts, maybe they become older again. And so we did these observations for thousands of galaxies. These are not